Hello, welcome to the next video in Advanced Mechanical Principles. This one we're covering outcome 2 and we're looking at stress and torsion. Today's session we're looking at part 1 of assignment 2, which is beams under stress. So we're going to analyse how beams bend when we put forces on them, basically. To complete this example you'll need your calculator, your trusty Casio calculator, a rule and some graph paper, because we're going to draw a graph of bending moments. Right. So what we need to do is look at what happens if we put forces on a beam. So I've got a beam, and if we look at this beam, then what's going to happen with this beam is as we put a force, in this case I'm putting a downward force on the top of this beam, then it's going to cause the middle to bend, as we can see in the slightly shaded. By bending, what's happening is the top half is being compressed, so this part is being compressed and made shorter, and the bottom part of it is being stretched or put under tension, and so will get longer. Now what this will cause is a curve in the beam. Okay, apart from what we get here is a part called the neutral axis. And the neutral axis is the part of a beam where, even though the beam's bending, its length has not changed, so it has no strain on it at this point. Always remember, strain is measured as the change in length divided by the original length. And so on the neutral axis there is zero strain. Right, okay, so what causes the bend, or more importantly, what causes it to bend more or less than the other, is a feature of beams called the second moment of area. Now the second moment of area, sometimes called the moment of inertia, okay, is used to determine how a beam's area is plotted around a three-dimensional axis. Okay, so the way we calculate it, the way we derive it, is very complex for you at level 3, but generally what we do is just remember these formulae, which will be given to you. I is the symbol for the second moment of area, and these calculations we're going to focus on this beam here, and then on the shafts exercise we'll be looking at these two functions here. But primarily we just need to remember I is equal to b d cubed over 12, where b is the breadth or width of the beam and d is the depth of the beam, or height, you might see sometimes. Okay, so let's just go back to our original beam. On this beam, the radius of curvature is effectively the distance. If I put some lines on here, then this beam, in bending, these vertical edges to the beam are now not vertical, and they will form a sector of a circle with the bottom or the top or any point in between. So we could pick it at this point here if we wanted, okay, halfway between the top of the beam and the neutral plane. But we're after the minimum radius of curvature, which will always occur on this bottom edge. Okay, the top edge, that will be the minimum radius of curvature of my beam. Apologies, I've just moved my, oh no I haven't. Okay, so this will be the minimum radius it bends. Okay, so for our calculation, the distance from our neutral plane is given the symbol y, and for everything we do, y is going to equal d divided by 2. Okay, and that is just summed up there. So y will always be d over 2 when we're doing calculations. Now there's a lot of things to calculate with beams. Factors of safety, maximum bending stress, and you have an example in the assignment you need to do. We're going to do an example that is like that. So I have a beam. We have upon this beam in blue a uniformly distributed load. So this load is 1 kilonewton per meter and is distributed over 5 meters off the beam. So every meter along this beam has got 1 kilonewton upon it. There's also a 5 kilonewton point force 3 meters away from this end. Okay. What we're being asked to do are these points. So the reaction forces R1 and R2, draw the bending moment diagram, find the maximum bending moment, calculate the maximum stress, from the maximum stress find the factor of safety, and determine the minimum radius of curvature for the beam. So, I'm going to start with the reaction forces. Okay, this is stuff we did last year in mechanical principles. You should remind yourselves that if we have a uniformly distributed load, as in blue, what we do is we resolve this uniformly distributed load to be a point load centered on its distribution of a force equal to its maximum point force. So we have a 1 kilonewton per meter force over 5 meters. So that will resolve to be a point force of 1 kilonewton times 5 meters, centered at 2.5 meters from both ends of the beam, because the UDL ran the whole length of the beam. So this, we can now work out what R1 and R2 are. And I'll try and keep my colours. So to start with, I'm going to label the edges of my beam. So I'm going to label that as point A and this end as point B. And we're going to start by making B the pivot of our beam. So we're going to take moments about B. Now you know me, I always like to do clockwise moments on the left, anti-clockwise moments on the right. And so clockwise moments, looking at this, R1 is going to push this beam clockwise if it's fastened at this end. This force is going to force it to turn in a clockwise direction. It is R1 strong and it is 5 meters away from the pivot. Therefore, we get 5 times R1 is equal to. Next force we come to is our 1 kilonewton times 5 meters UDL, which is centered 2.5 meters away from both ends. So it's 2.5 from this end, it is also 2.5 from this end. So we get 1000 times the 5 meters it's distributed along times the 2.5 meters it is away from point B. And added to that, also in the anti-clockwise direction, we have our red force, and our red force is 5 kilonewtons, and it's 3 meters from point A, so the distance from point B is 2 meters. So 5,000 times 2. So working all of these out, I get that 5 lots of R1 is equal to, in blue, 1,000 times 5 is 5,000 times 2.5 is 12,500 plus 5,000 times 2 is 10,000. And so, just resolving everything through, R1 is equal to 22,500 divided by 5, and so R1 is equal to 4,500 newtons. Okay, happy with that. Now we take moments about A, so I'm going to clear all this off. I'm going to shorthand myself, so moments about A. And taking moments about A, I'll put my A and B back in. This time R2 is going to be driving it anti-clockwise, whilst this force is going clockwise and this force is going clockwise. So I'm going to keep my convention. I like to have my clockwise forces on the left. So my first clockwise force from point A is 1 kilonewton, which is 1,000, times the 5 meters it acts, times the 2.5 meters it is from point A, plus the red force, and the red force is 5,000 times the 3 meters it is away from point A, which we can see there, and that is equal to 5 meters times R2, because R2 is acting 5 meters away from point A. So putting all that together, working this out, we get 12,500 again for my blue force, the UDL, plus 5,000 times 3 is 15,000, and that is equal to 5 lots of R2. And so R2 is equal to 27,500 divided by 5, and so R2 is equal to 5,500 newtons. Double underlining. So those are our two reaction forces. That's the first part of this task done. What we then need to do is draw a bending moments diagram from this. So what I've done is I've plotted this now on graph paper, and you need the bending moments diagram. But a lot of people will do what I've done here, which is to draw our beam to scale on the graph paper and then plot our bending moments diagram beneath it. Okay, so I'm going to work out these values and you'll hopefully see where these points have come from. Okay, the bigger or the smaller you make this gap in our calculations, the more accurate our diagram will be. Okay, but what we're going to do first is we take a line, we take our beam and we start at one end. Now I'm starting at this end, so I'm going to call this 0. Okay, and That's about straight. So at 0 meters, now I discount everything to the right hand side of my line. So all of this is ignored. And as you can see, I have no bending moment because my pivot is right at the end of the bar. There's nothing happening on this side, which is why we have 0 here. What you should always find with your bending moments diagram is it starts at 0 and it ends at 0 for a simply supported beam. So hopefully we're going to prove that. So what I then do is I move a given distance along my beam. So I could do 0.5 meters, but I've chosen to go in 1 meter steps because it's a nice, sensible value. So if I look at this in 1 meter steps, what in essence I've got, so at 1 meter, what in essence I've got for my beam, assuming it's supported, is 4,500 newtons pushing up and a UDL of 1,000 newtons per meter acting over 1 meter. If I resolve that UDL, that'll be 1,000 times 1 meter acting at 0.5 meters because it acts at halfway along. So if I work out my bending moment from this point here, I've got 4,500 times 1 meter acting clockwise minus 1,000 times 1 meter, which is the size of my UDL, times 0.5 meters from this point here, this line, 0.5 meters because it's in the middle, which is why I'm picking 1 meter steps. It makes life a little easier. So we'll see that the bending moment here is equal to 4,500 minus 500, which gives me a bending moment at 1 meter of 4,000 Newton meters. That is why I've got my plot here to be 4,000 newtons. Okay, so this axis, it was on my original diagram and I've cropped it off by mistake. This is my bending moment, bracket 1,000 Newton meters. So then move my line along another meter. So I'm now at 2 meters. And we do exactly the same process. So at 2 meters, what have I got? Well, I've got 4,500 from my reaction force. That's now acting 2 meters away. And going clockwise, I've got 1,000 newtons meter times the 2 meters it's acting, but now it acts in the middle of its action. It's going to act at the 1 meter point. So that's where my UDL will act at 2 meters. So we need to times by 1. Okay, so I get 4,500, I get 9,000 minus 2,000. So my bending moment at 2 meters is equal to 7,000 Newton meters, which again you can see from this point here. That's 2. Then I move along 3 meters. And I do exactly the same calculation. So I'll be able to fit this one here. Then I might have to clear what I've done. It's about 3 meters. My 4,500, my reaction force here is now 3 meters away from where we're pivoting. And my UDL is now 3 meters long. So I get 4,500 times 3 minus the UDL, which is now 1,000 newtons per meter, times the 3 meters it's acting, times the center of its action. So this UDL center's moved from 1 to 1.5. So it's 1.5. And what that gives me is 9,000. So that gives me 9,000 Newton meters, which again I plot on my graph. And this is why we tend to do the bending moment graph on scale below the beam. As you can see, I got my scale slightly wrong because I couldn't fit the beam on the words notable, but you can see where we're going. Okay, at 4 meters, this is where we start getting slightly tricky. So at 4 meters, I've now got 2 forces to worry about. So I'm going to redraw that one. So let's clear this stuff. Let's put my line back in. So my line is coming in at 4 meters. And this is where we've gone slightly off scale. So this should have been 3 meters here. 4 meters should be this one, 7,000 again. So if I draw this out, I'm going to put a rectangle in, make it a bit neater. Okay, what I've got here is going to be 5 kilonewtons acting 1 meter away. I'm going to have my UDL, which is now about there, 2 meters away from that point, which is also 2 meters away from that point, because it's in the middle of the action of this beam at 4 meters, and it is 1,000, 1 kilonewton times 4 meters. And we've got our reaction force of 4.5 kilonewtons. So if we look at the bending moment here, then we're going to have 4,500 times 4 meters minus 1,000 times 2 meters, times 4 meters times the 2 meters it is away from the pivot, minus 5,000 times the 1 meter it is away from the pivot. So 4,000 times 4,500 times 4 is equal to 20,000 minus 8,000 minus 5,000. And so that gives us a bending moment of 7,000 Newton meters at 4, which is this point here. And finally, at the 5 meter point at the very end of our beam, we should be getting a bending moment of 0. So let's just test that. So now our beam, let's just draw the beam again. Now what we've got is 5k acting at 2 meters. I've got 1k times 5 meters acting at 2.5 meters, and I've got 4,500 acting at 5 meters. So if I want to do my bending moment, I get 4,500 times 5 minus 1,000 times 5 times the 2.5 meters it's working from, minus 5,000 times 2. That one gives me 22,500 minus 12,500 minus 10,000, and so our bending moment at the 5 meter point is also 0 Newton meters. So our bending moment graph starts at 0, comes up and finishes at 0 again. And from the graph we can immediately see that our maximum bending moment is 9,000 Newton meters. That is the maximum bending moment, read straight off the graph. Everything else is now just done using one formula, or two formulae really. So if we move this on, what you then have to do is find the maximum stress due to bending. Well, now we've got the maximum bending moment, all we need is the second moment of area to be able to determine the stress. So if we come and have a look at this, okay, then the calculation is based around this equation. Okay, so what we need to do is define what these mean. So M is your max bending moment. We have just calculated that. I is your second moment of area. We are about to calculate that. Sigma is the max stress due to bending. Y is the distance from the neutral axis. E is your Young's modulus, or the modulus of elasticity. Modulus. And R is the radius of curvature. And we're going to be asked for most to work out with most of these. So the maximum stress due to bending, we need to know the second moment. So we've got the maximum bending moment, we know the distance from the neutral axis from our question, we need to know the second moment of area. Okay, so looking back at our question, we know that the breadth of the beam was 0.5 meters and the depth of the beam was 0.2 meters. That's in the question. Okay, so from that we can calculate that I is equal to B d cubed divided by 12. That is from the equation given to us earlier in this video. Okay, plug our numbers in. I is equal to 0.5 times 0.2 cubed divided by 12, and my second moment of area for this beam is 3.33 recurring times 10 to the minus 4 meters to the power 4. So the unit of second moment of area is meters to the power 4. With that in hand, we now know we can also work that y, remember what we said earlier, that y is d over 2, y will be 0.1 meters. So what we've now got with this expression, okay, is we know our maximum bending moment, m was 9,000 Newton meters, I is 3.33 recurring times 10 to the minus 4 meters to the 4, y is equal to 0.1 meters. We plug all of that in, we can see that we get 9,000 divided by 3.33 recurring times 10 to the minus 4 is equal to the maximum bending stress we don't know divided by 0.1. And rearranging that gives us that sigma is equal to 9,000 times 0.1 divided by 3.33 recurring times 10 to the minus 4, and our maximum bending stress is equal to 2.7 megapascals. Okay, so we've now got our maximum bending stress. What we then need to know is work out what the factor of safety is. So the factor of safety brings in the ultimate tensile stress. Okay, the ultimate tensile stress, if we remember, just sketching loosely, when we exhibit a material under stress, it'll follow a straight line and then it'll do something like that and then it'll break. This is called the yield point. And that's really the point where it'll stop being an elastic and it'll become a plastic transition. This point here is the ultimate tensile strength, or ultimate tensile stress. Okay, the ultimate tensile strength is how much it can take. Okay, so we've got stress against displacement. Okay, the UTS is how much stress it can take before the displacement gets out of control. Okay, how much we can put it under to still be safe, but we wouldn't want to then use that thing again because it's deformed but it hasn't broken. Okay, so in our example for UTS, it's given in the question 30 megapascals. Okay, we've just calculated M 2.7 megapascals. So the factor of safety is a very straightforward calculation. 30 times 10 to the 6 divided by 2.7 times 10 to the 6, and that is equal to 11.1. So this device has a factor of safety of 11, which means you can go 11 times that stress before it will break. Okay, last thing we're going to do, the minimum radius of curvature. So we're only going to use these two parts of the beam equation. We can use the others if we want, but these are the ones we happen to have to hand. Okay, so we know what M is. M is 9,000. E is given to you in the question, and R is what we're after. So if we plug in what we know, M is 9,000 Newton meters. I is 3.33 recurring times 10 to the minus 4 meters to the 4. E is equal to 50 times 10 to the power of 9 pascals. Plugging that in, we get 9,000 divided by 3.33 recurring times 10 to the minus 4 is equal to 50 times 10 to the minus 9, make that 9 a bit better, divided by R. So rearranging that, R is equal to 50 times 10 to the 9 times 3.33 recurring times 10 to the minus 4 divided by 9,000, and we have a minimum radius of curvature, comes out as 1.85 times 10 to the 3 meters. So our beam's radius of curvature is 1.85 kilometers, which means it really hasn't bent an awful lot. It's probably displaced by a millimeter or two. Okay, now for the merit task on this, what you're going to be asked to do is to look at how changing your size of your bar affects the radius of curvature. Okay, so I would recommend using Excel again, and from it developing a table that calculates the radius of curvature, calculates the second moment of area for different values of D and different values of B using the equation. Then build that table up so it works out the minimum radius of curvature and the stress, and look at what the graph shows you in the shape of the graphs. Okay, then look at the formula and put the two together to explain why. If you're struggling with that, we'll do more when we get back. Okay, but that's everything I want to do today. Thank you and enjoy.